Inside a high-frequency power system, raw electrical energy constantly pulses through a dense, microscopic crystalline lattice structure at absolutely extreme velocities. Modern power electronics depend on gallium nitride high-electron mobility transistors, or HEMTs. These devices rely on a two-dimensional electron gas, a highly conductive layer that allows carriers to move with high mobility. However, conventional GaN HEMTs face a recurring physical limitation. They exhibit high gate and drain leakage currents, often losing power in the milliamp per millimeter range. Much of this leakage is caused by trap-assisted tunneling. Electrons bypass the Schottky barrier using surface defects as stepping stones to migrate across the physical gap. This migration bleeds power and introduces thermal instability, making it difficult to maintain efficiency as the technology scales. In 2017, a study by Hassan and colleagues investigated a specific structural intervention to address this leakage floor. The researchers integrated a 10-nanometer layer of silicon dioxide into the gate stack, creating a metal oxide semiconductor, or MOS HEMT. The study aimed to determine if this dielectric could suppress tunneling while maintaining the high electron mobility required for power applications. By applying spectral noise analysis, we can look past the surface performance and identify exactly how this oxide layer interacts with the underlying semiconductor. Without a method to resolve interface flaws, the operational limits of gallium nitride are physically constrained by the very barrier intended to control the current. The baseline architecture of these devices consists of an undoped gallium nitride layer, a 1-nanometer aluminum nitride spacer, and a 20-nanometer aluminum gallium nitride barrier. Panel C shows the modified MOS HEMT structure, where the 10-nanometer silicon dioxide layer was added via atomic layer deposition to act as a gate dielectric. To analyze how the material composition affects leakage, the researchers tested aluminum mole fractions of 20% and 35%. This diagram compares the compositions. Increasing aluminum to 35%, the black lines, widens the band gap and increases the electric field compared to the 20% in red. While this increases carrier concentration, the resulting band bending is more severe, scattering carriers and reducing mobility. This steeper gradient also increases the probability of carriers tunneling through the barrier when the device is in the off state. Higher aluminum concentrations create more conductive channels, but they also result in inherently leakier devices unless a physical dielectric is present to block the path. We can observe the result of this band bending in the direct current performance of the device. One primary metric is subthreshold swing, which measures how much gate voltage is required to change the drain current by one order of magnitude. The data shows that higher carrier density often comes at the cost of barrier transparency, necessitating a physical dielectric to maintain control over the current. Now we can compare the performance of the conventional HEMT against the SiO2 MOS HEMT directly. These transfer characteristics show the standard HEMT in blue, which fails to fully pinch off current even at high negative gate voltages. Because of this high leakage floor, the conventional HEMT achieves an on-off ratio of only about 10 to the power of 1. When we look at the black curve for the MOS HEMT, the drain current drops sharply, stabilizing at 10 to the negative 11th amps per millimeter. This represents an 8-order of magnitude improvement in current suppression, achieved by the 10-nanometer silicon dioxide layer. The MOS HEMT also shows a sharp subthreshold swing of 72 millivolts per decade, suggesting a much more efficient switching response. This is confirmed by the gate leakage data. The standard HEMT begins to leak significantly at just 0.5 volts, while the MOS HEMT remains stable until 4.25 volts. The silicon dioxide layer is physically obstructing the path of the electrons, preventing them from migrating from the gate into the AlGaN layer. To see if this improvement is a surface-level change or a change in the bulk material, we turn to noise analysis. The DC data demonstrates the scale of the leakage suppression, but spectral noise analysis identifies the physical location of the defects responsible for it. Low-frequency noise serves as an electrical signature of physical defects within the semiconductor structure. Typically, a clean device follows a smooth 1/F trendline, where noise power decreases as frequency increases. Comparing the spectral noise of the standard HEMT against the MOS HEMT reveals clear differences in their internal defect profiles. In panel C, the standard HEMT shows a prominent generation recombination bulge at 550 Hz. This bulge is the electrical manifestation of carriers being trapped and released by defects within the AL-GaN layer at that specific frequency. In contrast, panels A and B show that the MOS-HEMT profile is significantly cleaner across the spectrum. The generation recombination bulges are pushed to much higher frequencies, up to 4,000 Hz, making them negligible for most power applications. The vertical axes also show that the absolute noise floor of the MOS-HEMT is an order of magnitude lower than the conventional device. We can interpret these findings by applying the carrier number fluctuation model. Because the oxides layer eliminates the acoustic signature of these traps, results suggest silicon dioxide is passivating the surface defects that drive the noise. This raises the final question: is the device noise caused by bulk material fluctuations or by trap states at the surface? We can use the carrier number fluctuation model as a test. If the noise is a surface phenomenon, it will follow a specific mathematical relationship. We plot the noise spectral density against the drain current to see how the device behaves. Panel C shows that the data points align precisely with the square of the transconductance divided by the drain current. This alignment with the purple circles provides mathematical evidence that the noise is a surface-driven phenomenon. The noise originates from the dynamic trapping of carriers at the AL-GaN SiO2 interface, rather than from defects within the bulk gallium nitride. We can benchmark the overall noise performance using Hooge's constant. The conventional HEMT has a Hooge's constant of 0.05. The MOS-HEMT reaches 0.005. This indicates that the 10 nanometer silicon dioxide layer reduces the fundamental noise floor of the device by a factor of 10. By integrating this thin dielectric, the researchers suppressed the gate leakage floor and passivated the surface, resulting in a MOS-HEMT with stable noise profiles and improved high power efficiency.